All right, thanks for watching. And today I want to talk about a concept that probably exists already, but I kind of came up with it myself. But you'll see it's kind of trivial, but it's what's called the product integral, or you can call it the Peyam integral. And all it is, it's just a regular integral, but instead of summing up the values of f, you just multiply the values of f. So, let me recall a bit the concept of Riemann integration. And by the way, this only works for positive functions for obvious reasons. So you'll see. So, let me just recall again the steps of Riemann integration. So suppose you have an interval AB. Then you can, for a given n, you can chop the interval up into n pieces, where the width is b minus a over n, and you get points xi, which is a plus I delta x. Okay, so this is x0 if you want, x1, x2, x3, dot, dot, dot. And at every point, in every little chunk, you pick a random point called xi star. So xi star, it's a random point, I believe, in xi minus 1 comma xi. Okay, and that's for all I equals to, I think, from 1 to n. Now, the Riemann sum, so the Riemann integral just says that the Riemann integral of f of x is equal to the limit as n goes to infinity of the Riemann sum. Sum from 1 to n of delta x f of xi star. So you pick a random point in this interval, you sum up the values of f, and you multiply it by this factor of delta x. If this is true, independent of xi star, independent of your choice, then the integral exists, and we call it the Riemann integral. So integral of f of x dx. Now, the only modification for the product integral, which I'll define now, is instead of doing the sum, you do the product. So you're doing pi of 1 to n of this thing. And also, it turns out if you do that, I think you will always get 0. So just to normalize this if you want, and you'll see why it's the correct analogy, you wanna, instead of multiplying f by this little delta x's, you will exponentiate that. So this is what I call the product integral. The product integral of f of x dx is the limit as n goes to infinity of the product of, from 1 to n, of f of xi star delta x. And again, all that this means, it's f of x1 star over delta x times f of x2 star to the power of delta x dot 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 f of xn star to the power of delta x, and you just let n go to infinity in this infinite product. Alright, and as I said, I haven't seen this feature before, but the reason you haven't is because turns out, once you define this product integral, you can just rewrite it in terms of a Riemann integral in the following way. Because, so what is the relationship with our regular Riemann integral? With our usual integral? Because, well, by the way, I want to say this is not a stupid idea, because it's still interesting to see what if you, instead of summing your function, you multiply them. Turns out, interestingly, you can rewrite this in terms of a Riemann integral, and the reason is, what do you need to transform a product into sums? Well, just ln. So take now ln of the product integral. So ln of the product integral of f of x dx What is that? So, by definition, it's ln of the limit as n goes to infinity of the product from 1 to n of f of xi star to delta x. Okay, now let's cheat a little bit. Let's not be quite rigorous, but assume you can put ln inside that product. And that's okay if the product is non-zero. So because ln is continuous at every point except for 0, you can pass inside the limit. So assume we can pass inside the limit. And this is also why we require f to be positive. Otherwise, this doesn't make sense. So that's limit n goes to infinity of ln of the product from 1 to n of f of xi star to delta x. Okay. Now again, this is just a product. So if you take ln of a product, it becomes the sum of ln's. So limit n goes to infinity of the sum from 1 to n of ln of f of xi star to delta x. Now, again, it's ln of a to the b. So this just becomes ln, limit n goes to infinity, of sum from 1 to n of delta x, ln of f of xi star. And now, compare this to the Riemann sum. Riemann sum is limit n goes to infinity of the sum of delta x f of xi star. Well, it's the same thing except with ln. So this actually becomes the integral from a to b of ln of f of x dx. So ln of the product integral is the regular integral. So the product integral is just e of the regular integral. So it turns out it's not quite a new concept. So e of integral from 0 a to b of ln of f of x dx. And if you like algebra, good for you, okay? Notice this is precisely conjugation by ln, because you do ln integral and then inverse of ln, e, but did not help me so far in life, but still, it's kind of neat. So the product integral is e to the integral of f of n, ln of f. And so let's just calculate a couple of examples, and then we'll just do a couple of more properties. So the third part is just examples. Step 3. Using or not this formula, okay? So let's take f of x equals to 1. Let's see what is the integral, the product integral of f. Well, that's e to the integral from a to b of ln of f, so ln of 1. So product integral of 1 is equal to e from a to b of ln of 1 dx. This is 0, which becomes e of 0, which is 1. Which is obvious if you think about it, because you may ask, what happens if you multiply 1 a bunch of times? Well, if this is exactly 1, you should get the answer 1. So we didn't even need that formula. So in other words, for the product integral, 1 plays a new role of 0. Because the Riemann integral of 0 is just 0. Here the product integral of 1 is just 1. What if we have a constant? How does that behave? So f of x equals to c. Then let's see. C, senor. The product integral of c, again positive, is just e of from a to b of ln of c. And that's e to ln of c from b to a, b minus a, and that's just c to b minus a. So it's already interesting. In particular, the integral of a constant is not constant times the integral of 1. It's constant to the length of the interval. And again, you can check it using the definition. It's not too bad. It's because it's c to the b minus a over n, but if you do this n times, you get c to the b minus a. Okay, something slightly non-trivial. F of x equals to x. What happens if you multiply x a bunch of times? So e of integral from a to b of ln of x dx. Well, that's e to the, remember, antiderivative is x ln of x minus x from a to b. And that's e b ln of b minus a ln of a minus b plus a. So plus a minus b if you want. And I believe this is e to the a minus b and then b to the b over a to the a. How cute is that? The product integral of x is this weird thing, huh? Who would have thought? Okay, now, couple of other examples. So remember e to the x was very nice with the product integral. So let's see what that equals to. Okay. Now the next one, let's do it directly. Let's do it using the formula and let's do it directly. And because the reason is directly is also kind of nice. So integral, so product integral of e to the x dx, that's e to the integral from a to b of ln of e to the x dx. That's e to the integral from a to b of x dx. And that's e to the b squared minus a squared over 2. The antiderivative is x squared over 2, and then from a to b, that's b squared minus a squared. Let's do it directly, because it's also kind of neat. And that's like one of the only examples where it's nice to do it directly. So, here I am. So the product integral of e to the x, that's just the limit from n goes to infinity of the products from 1 to n of a random point e to the xi star delta x. Okay, now assuming that this product integral exists, and I guess it's not clear when it exists, I guess it exists when ln of that is integrable, so that's fine. Let's just pick xi star to be xi, which is, I like to remind you, a plus I delta x. Now, let me see, then we get limit n goes to infinity of pi. So the product from 1 to n of e to the delta x times, in this case, xi. So we chose xi star to be xi. And then remember, the product of a bunch of exponentials, like e to the x times e to the y, is the e to the sum of exponentials. So this becomes limit n goes to infinity of the sum from 1 to n of e to the delta x. Sorry, e to the sum of it. So e to the sum from 1 to infinity is 1 to n of e of delta x times xi. Okay. Now, let's deal with that sum. So that's equal to the sum from 1 to n of, let's see, b minus a over n times, so xi is a plus I times b minus a over n. And well, let's see. So we can pull this b minus a over n out. And then we get sum of a from 1 to n. And that just becomes a times n. Which simplifies to b minus a times a. And then this other term, so b minus a over n comes out once, comes out twice, so squared, times the sum of I, which is just, remember, n times n plus 1 over 2. So in the end, what we have, this becomes, we can rewrite this, b minus a squared over n squared over 2 over n squared. Okay. And now, the next step is, of course, to let n go to infinity. Now, as n goes to infinity, this is still b minus a times a. It's just a constant. And this term, notice, this is almost like n squared over n squared, which is 1. So it goes to b minus a squared over 2. And it turns out you can simplify this. So sorry for doing it here. But let's simplify that. So this becomes b minus a times a plus b minus a over 2. And this becomes, so a is 2a over 2. 2a plus b minus a becomes actually just a plus b. So we get b minus a times b plus a. And that's just b squared minus a squared. Sorry, over 2. B squared minus a squared over 2. So in the end, we do get e to the b squared minus a squared over 2. Which is exactly the answer that we got here. But I just want to show you, in this case, it's very cute because we get, e, the product of exponentials is exponential of the sum. So it's one of the neat cases where it's nice to do it directly. Okay, one more example and then just some quick properties. Turns out you can do the same thing with sine, and it's not a big, it's not so surprising because usually stuff you can do with exponentials you can do with sines. So let's do f of x equals to sine x on 0 comma pi. On the one hand, you can do, well, integral, that the product integral, of sine equals to e from 0 to pi ln of sine of x dx. And that equals to e. I have done a video on this, so if you're curious, you can look at the video, and it becomes e to minus pi ln of 2, which you can just write as 1 over 2 to the pi. Either you watch the other video, or let me show you another way of calculating this integral, which shows you why we have this. Because if you do it directly, right, what is the product integral of sine? It's just the limit of a bunch of products. So, and let's do some product from 1 to n minus 1 and explain why. So sine of xi star delta x. Again, just choose xi star to be xi. So xi star equals to xi, which is a plus I delta x. But here a is 0, so it's I delta x, which is I times pi over n. And the reason I just did it from 1 to n minus 1 is because if I is n, you get pi, and you get sine of pi. So in that case, it would be 0, which is not interesting. So think of it as an improper, if you want, an improper product integral. And I think same with at 0, but here we don't really care because we choose the right one. So this then just becomes limit n goes to infinity of sine of pi over n, sine of 2 pi over n, up to sine of n minus 1 over n pi. All this to the power of pi over n. Now, notice this involves a product of a bunch of sines, but I think this video is just advertisement for other of my videos. I've actually done this, so a video on the product of sines, and the result that you get is it equals to the limit as n goes to infinity of n over 2 to the n minus 1 to the pi over n, and then that's just equals to limit n goes to infinity of n to the pi over n over 2 to the n minus 1 pi over n. Now this thing, limit as n to the pi over n, that's one of the calculus limits which you'll do usually by L'Hopital's, and the answer is 1 to the pi, which is 1. And this n minus 1 over n goes to 1, so it's 1 over 2 to the pi, which is, lo and behold, exactly the same thing as we got here. So if you didn't know what the integral here is, well, here I rederived it. So it's kind of cool. Last but not least, just a couple of quick properties. So I think that's, let me see, what step was that? I don't even remember, but I think step 4 maybe. Properties. And I think this is why product integrals are so nice. First of all, what is the product of a product integral? Well, you can either do it using the definition or using the formula. Well, that's e to the integral from a to b ln of fg. That's e to the integral from a to b ln of f plus ln of g. Like that if you want. And that's just e to the integral from a to b of ln of f times e to the integral from a to b of ln of g. But that's just the product integral of f times the product integral of g. So here's the cool thing. A product integral of a product is just the product of a product integrals. So, yo dog. Or in other words, that's what's called a homomorphism from multiplication to multiplication. And using this and the fact that the integral of 1, product integral of, I think 1 is 1, you also get that the product integral of 1 over f is just the product integral of 1 over the product integral of f, which is just 1 over the product integral of f. And you just use the fact that f times 1 over f is 1. And you apply product integrals on both sides. And using that, you also get that the product integral of f over g is the product integral of f over the product integral of g. So how nice is that? It's sort of like the exponential derivative. It's like an exponential integral, if you want. And also, you can also use the definition, and you find the product integral of f to the c is the product integral of f to the cth power. And if you want, for the case where c is a positive, is any integer, you can just use this property. And, however, be careful, the product integral of cf, well, that's the product integral of c times the product integral of f. That's c to b minus a times the product integral of f. So it's generally not linear, unless in this case if b minus a is 1. Then I think you're fine, but in general the product integral of a plus b is not the product integral of a plus the product integral of b. So generally they are unrelated. Alright, and that's all I know about product integrals. So particularly, I don't know what they're useful for, sorry, but if you have any other ideas, I'd be happy to listen to them. And if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.